Okay, so today we're going to first start with looking at the problem I didn't have time to do last class period that is part of the homework set. And then we're going to go on to Gauss's Law. It's pretty easy with one student. I know exactly where to look. Now, before I actually get to Gauss's Law, I want to make sure that you are aware of the homework that's due next week for the calculus. I mentioned it last class period, but I want to actually look at it real quickly.
Where is it at?
It is on Moodle, I believe, but I need to update it. I updated, so I have a slightly different version here than what is on Moodle right now, so I need to update that, and I have a rubric as well. So here are your questions. Question 1, a semi-infinite wire, a wire that goes from z equals 0 to z equals minus infinity, and has a constant linear positive charge density, lambda. And so this you have for part A. Now notice, draw a sketch, use a ruler, right? Don't make it rough like what I'm going to draw. Here's my rough drawing, right? That ain't right. And you need to identify the x-axis and the z-axis. Here's your origin. And for the first part, yeah, Alex, you be late. And I know you weren't at chapel.
Oops. I didn't actually think I was late, but unfortunate. I'm going to blame my roommate because he had to have a conversation with me on my way out. I was leaving with exactly enough time to get here.
One should never have a conversation with the roommate, huh?
But I got to explain to him the difference between convection and conduction of thermal energy.
Okay, well, I mean, that is valuable.
It is.
And he's not late on attendance.
Well,
Yeah, because I was already
that's
doing physics.
not quite right, but...
I was doing physics before class started.
Okay, so your geometry is something like I've drawn here in this picture. But remember, you have to do it carefully using a ruler, right? I don't want something sloppy like this here done quick freehand. And so it has steps here for everything you need to do going through. Now, to make sure you understand how it's going to be graded, I also have a rubric here. So here is the rubric. So you can see how I'm going to divvy up the points. So if it just has a dot there, it'll just be 1 point. If it's different than 1 point, it will have a bracket and the number of points in it. So it'll be 1 point for having an accurate sketch, and it's either 1 or 0, right? So if your sketch is done by freehand, not with straight lines, then you'd get a 0 for that. Coordinate system identified, 1 or 0. Direction correct for the electric field due to a little piece needs to be in the right direction. And so you can see where each of the points comes from. You'll definitely want to look like there are places where it says, what assumptions do you use? And here I say, how many assumptions? And I even say based on symmetry. So you'll probably want to look at this rubric as you're doing your solution just to make sure that you have everything in there. So I've already told you the first problem is dealing with Coulomb's law. After that, you're going to have to, some of them ask you, are you going to use Coulomb's law or Gauss's law? And if you're using Gauss's law, you're going to use the differential form or the integral form. So let's get back to the lecture here and talk about these things. So first, if you want to look at what the textbook has on this material, it's section volume 2, 5.5 of the textbook. Once again, because I didn't pay a lot of attention to your textbook being different from the other textbook last semester, here is your textbook, volume 2, you see up there at the top, volume 2, and this is section 5.5, and you see it says that you have, if it's a linear charge density, a surface, I said areal, I said lineal, I think as well, charge density, or a volumetric charge density, then you have these different symbols for the charge density. And this is how you calculate, I can't write on this, this is how you calculate the electric field. Now, what is different from this and what we did last week is last week I was talking about Coulomb's law, which is the equation for the force between 2 point charges. This is still Coulomb's law, but it's the electric field due to a single charge. What's the difference? You just divide one charge away. And so what is 1 over 4 pi epsilon 0? What is that to you? Yeah, that's just that constant k. We write the constant k because it's shorter to write than 1 over 4 pi epsilon 0. But k is defined as 1 over 4 pi epsilon 0. Then you have the integral over the line of lambda dl over r squared, r hat. It is a vector. That's why there's the r hat. I told you very quickly, I take my dE, I calculate dE first, and then I find the components of dE, the x component and the y component. So I never actually write it like that with the r hat for my integral. I break into the x component and the y component, and then have an integral for x direction and an integral for y direction. And so the same would be true for area, then it's going to be sigma dA, and for volume, it's rho dV.
So I think what I'm most worried about is my ability to identify the L, dA, and dV, as in like figure out what they mean. So dV would be dx, dy, dz?
If it's Cartesian coordinates, yes. I'm going to look at a couple different situations, hopefully in class today. If not, then we'll do it in class next week, where we're going to use cylindrical coordinates and spherical coordinates. So it won't be just dx, dy, dz. And now you're in calculus 2, you're probably just getting into doing double integrals or something, right?
We're in Calc 3, but we haven't done any double.
Oh, okay. You're Calc 3 and you haven't done double it? Okay. The different arrangements. Yeah.
If you like shapes.
Okay, so this is the discussion here in the textbook. You see here example 5.5 electric field of a line segment, and come down here. There's example 5.6, which is exactly what I'm going to do. Actually, well, I'll do something that's like 5.5 or 5.6, but you'll see I do my calculus differently. I do my calculus differently because I think it's a lot easier than their calculus. It takes a little creativity to make it an easier problem. So let's go ahead and get back to what I'm going to do. I'm going to solve this problem, which is essentially 1b. 1a is the easy one. 1a should go very quickly as long as you understand. If you don't understand, obviously talk to me and get some help, right? Don't say, I can't do this homework. Talk to me. The homework assignment is one that I had a student who was taking electricity and magnetism at UNL, and the teacher said, here's stuff that you should have learned in your college physics class on electricity and magnetism. Well, on electricity specifically. And so I figured, well, if that's what he figures, this is a minimum what you should have learned. That's a good assignment to give you. Make sure you can do what he considered a minimum of what you needed to learn. So here I have a charge on a line. Now you will notice that this is different from your homework problem in that I have a line of indefinite length here. Your homework problem is a semi-infinite line. It's a line that will start here and just go in one direction off to infinity and not go the other direction at all. So there is a difference. I'm not exactly doing your homework problem. Also, the orientations are switched. Your line is along the z-axis in the homework problem, whereas here the line is along the x-axis. Not a big deal. Okay, so the first step that we have to do, let's just look at the problem real quick. Whoops, that was not what I wanted. No, it is what I wanted to do. Hey, sometimes you make a mistake and you do it right. So the first step is to draw a sketch using a ruler, include the wire, the x and z axis, the point P, put an arrow indicating the direction of the electric field due to a small segment, well, due to actually the entire wire. So you're going to draw that in. For my segment, because I don't have it defined how long it is on either direction or if it goes to infinity on either direction, I can't do the entire electric field vector. But that's what you're supposed to do. You're supposed to have, so for instance, with this here, if this is a positive charge evenly distributed along this wire, what direction is the electric field going to point at A? Does the electric field go into positive or out of positive?
Oh, it goes out.
Goes out of positive because it's the direction that the force would be on a positive charge. And so positive would be repelled by positive. So this here is one dimensional. So that one's easy. That one's just like that. Now the next one, for part B, I'll just put point B over here. You have point B over here, some distance B away. Well, for that one, it's not so clear cut because you have the direction from the very top would be going like this. The direction from the very bottom would be going like this, but very weak. And so you know it's going to be somewhere between those two, and you need to estimate what direction you think it will be. In the end, you will get the answer. But you should have two components, one that is going in the x direction, one that's going in the z direction. Okay, so now looking at what we are supposed to be doing here, what ideas will you use to determine it? Well, I told you for number one, we're going to use Coulomb's law. So that's my idea, Coulomb's law. And then sketch the infinitesimally small element and say if it's a line element or a volume element. Make sure you look here. What are you going to get points on? Is the element identified? Did you draw it? And did you identify that it's a line, area, or volume? So going to my slide here, the element is shown here in blue. That's dx. Is that a line, an area, or a volume? It's a which?
A line.
It's a line. That's right.
So element means the tiny amount of...
It's the element is the tiny thing that we're integrating. So we're going to be integrating over dx along the line. If it was aerial, it would have had dx dy and it would be integrating over the area of the surface. So just look at the units. It has units of distance, hence it's linear. Okay, so from this piece, I have dE shown like that. Now I need to come up with an equation for dE. So the magnitude of dE, I didn't put a vector sign, so it automatically means it's the magnitude. What's the magnitude going to be? Equation form. Always dE equals Coulomb's law.
Q1, Q2 over R squared.
Okay, that's the force between 2 point charges. So we're going to divide out the Q2. So it'd be just K Q1. But now we're doing the differential form. It's a D. So it'd be K dQ over R squared. Now, because we have a line element, dQ is equal to lambda dx. And so I put that in and I have dE. My D's are just horrendous. Now that dE is in terms of two variables. One variable is x and one variable is r. R is dependent on x. In fact, I can do this real quick. R squared is going to be y squared plus x squared. So I can find a quick relationship between the two, but I'm not done. So I'm not going to find a relationship yet. Because now I need to break dE up into the components because it's actually a vector. So dEx and dEy. So I'm just going to have dE times, and I'll use my trigonometry. So you see how theta is defined. X is going it doesn't have positive directions marked, so let me make positive directions explicit. Oh boy. Okay, so there I have my directions explicit. So if we look at the DEX, is that going to be sine or cosine of theta to get the x component? It's going to be sine because that's the opposite side. And we have to, by tradition, this is a negative angle, right? So sine of a negative angle is negative. And so as long as we consider that a negative angle, then that's going to be dE sine theta. Your definition of the angles is important, of what's positive and what's negative. Okay, and what about the y direction? dE times
Angle.
cosine is right. What did you say?
On the angle. So we're defining it from the y-axis, though?
Yeah, we're defining the angle from the y-axis, and actually, I was wrong. We do normally consider that positive. We consider it positive if it's going counterclockwise. And so if that's a positive angle, I need to put a minus sign here. Kind of mistakes. I made 2 sign errors last class period. Yeah, you have to pay some attention. So it's going to be a positive angle on this side. Hence, I got the sign now right.
Okay.
Go ahead.
So that means when we have a negative theta, right?
Mm-hmm.
That means our x is going to be negative? We define x as to the right is positive.
So when we're taking a piece out here that's a positive x, we're going to have a positive angle and DEX is negative. When we take a piece over here that's at a negative x, we're going to have a negative angle, and that's going to make it a positive DEX.
So that changes things.
Now let's combine, put this in for DE. And so DEX is equal to minus K lambda dx over r squared sine theta. And DEY is K lambda dx over r squared cosine theta. Now how many variables do I have in my integral? 3. And we all say, hooray, this is great. How many variables can I have in integrate? 1. So I have to eliminate 2. I have to find a way to combine them. And there's more than one way to skin the cat. The textbook eliminates everything but x. So the textbook, well, how do you decide? You decide by saying, what relationships do I have between these 3 variables? And I have actually 4 relationships. I have r squared is equal to x squared plus y squared. I have sine of theta is equal to, and I'm just going to look at the picture to make sure it's right. Sine of theta is going to be opposite over hypotenuse, so x over r. Cosine of theta is equal to adjacent over hypotenuse. Tangent of theta is equal to opposite over adjacent. So I have these 4 relationships that I could use to eliminate 2 variables. And as we've seen, the textbook is going to say, okay, let's put everything in terms of x and y. And so cosine theta, or not x and y, x and y. And so let's take cosine theta and say that's y over r, where r is square root of x squared plus y squared. And sine theta is x over r, where r is square root of x squared plus y squared. And then we're going to have it all in terms of x. And we'll be done. And you can do that. It doesn't look that bad, but the integral you're going to have to look up in an integral table. So there is an easier way of doing this. The easier way is to say, okay, I am going to put it in terms of the angle theta. And so if I'm going to put it in terms of the angle theta, then I can take this relationship here and substitute that r is equal to y over cosine theta. Now remember, y is a constant because that's the distance we are away from the line at its closest approach. And theta is the variable I want. So that's one relationship that will allow me to replace r. But I also need to be able to replace x. And that one is the one that really is the tricky one. You take the derivative of the tangent equation. Most people would not have thought of this, right? So it's a trickier solution. But what's the derivative of tangent theta? I only know because I look it up before doing this lecture. Dude, that's correct. Now, I didn't say with respect to theta. I just said the derivative. So what this gives us is secant squared, which is 1 over cosine squared, times d theta. So d theta over cosine squared of theta is equal to, since y is a constant, that's just dx over y. So now I can say, aha, from this work, I'm going to use dx is equal to y d theta over cosine squared theta. And I'm going to use, I missed a dot there. Well, I'm going to use r squared is equal to y squared over cosine squared theta. I had dx over r squared, so combining those, and look what happens with those cosine squared thetas. What do? They cancel. And one of the y's cancel. So dx over r squared turns out to just be a constant y times d theta.
Isn't that d theta over y?
You're right. It's over y. D theta divided by a constant y. Good catch. I would have gotten to the end and say, wait, my units ain't right. So now I can do these integrals with relative ease. Minus k lambda over y times sine theta d theta and equals k lambda over y times cosine theta d theta. So if I want to find, remember the top one is dE in the x direction. So if I want to find E in the x direction, what do I do with that? If that's dE, I just integrate.
But would the limits have problems?
We have to pay attention to our limits. So I'm not putting in the limits right now, but I will in just a moment because it's very important. Now, without the limits, we can do the integral. Integral of sine is going to be minus cosine. So that minus will get rid of the minus out front. And I have to put my limits. And the integral of cosine is sine. And I have to put my limits. So now we go back to our original picture and we say, what are the limits? And so let us suppose that we go from a distance A out here to a distance B out there. So the angles are going to be, the lowest angle will be starting here. So I'm going to put this one as my lowest angle. So I'll have theta min. Going to have to use trigonometric functions, right? And so my theta min is going to be defined by using tangent. So arctangent of minus b over y. And theta max will be tangent, arctangent, of a over y.
Now, would it be possible, or would it be considered incorrect to do that intuitively by knowing that if it's going off in infinite, then the angle is going to approach 90?
That's perfectly fine, yes. And so that's what you're going to be doing in your homework problem. You're just going to be saying, okay, so it's going to go from an angle of minus infinity or minus 90 degrees to 0.
Well, it can't go from actually 90 degrees though, right? It can't actually go.
That's the limit. If it's going to
That's the
infinity,
limit.
you're in the limit up, which is what your limit is. It's the...
Okay, so it actually hits the limit because it's going into infinity?
Well, that is the limit. When you're doing the integral, you're doing the integral to a limit.
I mean, not limit as in the bounds, I mean limit as in...
But they mean the same thing. And so we have our limits here. B over y and a, and so on for the others. Because this one is cosine, I'm going to come back to the picture and just figure out what cosine is at maximum, cosine at minimum. So the cosine is going to be positive in both cases. And cosine maximum would be y over square root of b squared plus y squared. And cosine minimum would be and cosine is positive in both cases. So it should be that. And for sine, excuse me?
How is it positive in both cases?
Because the cosine of the angle is positive if you're symmetric about 0. So as long as you're in the fourth or first quadrant, which is what we're in, cosine is going to be positive. And the sine is going to go from, for the minimum angle, it was minus b over so have something like that. Now, somehow I feel like I have once again inverted my signs. How do I get my signs wrong every single time? Right, because this is clearly a negative for the electric field in the y direction when we know it's a positive. There's something.
If you go back, back more, like all the way to the picture. You're saying the cosine is positive, but isn't the direction negative to get down to the y? Does that have anything to do with it? I'm not sure.
I'm considering this y a positive number.
But you define y as not positive.
Yes, but in terms of finding the angle, I just used the magnitudes of these sides.
Okay, so that wouldn't affect where we got the sine.
I'm going to have to sit down and figure out where I'm making all these sine errors because it's kind of ridiculous. But that's how we would do this. Now, for your case with the semi-infinite, you're just going from 90 degrees to 0. It comes out real simple, right? Because cosine of 90 degrees, cosine of 0, sine of 90 degrees, sine of 0. Those are easy things. So that's how you're solving 1b. Hopefully you don't make sign errors. If you do, you have to go back and try to figure out, which is what I'm going to do after class. I will sit down and figure out what in the world did I do here to get my signs wrong. But that's how you do it. Do you have questions about how to do it?
Just go back over to the answer.
I have a question about lab. Is that okay to ask now?
Let's talk about it after class. Okay, good? Okay. Now going on to chapter 6 of the textbook, talking about Gauss's law. Carl Friedrich Gauss came up with, and we see this a lot in electricity and magnetism. He came up with a really brilliant law based on something that we've actually already stated. He said that the electric field coming out of a region is proportional to how much charge is in that region. I said that in class Friday, that the electric field coming out of a charge, the number of lines is proportional to the charge. And that came simply from using Coulomb's law. So Gauss said, okay, so the number of lines coming out is proportional to the amount of charge. I can take any region, and if I just measure how much electric field strength is coming out of that region, I can tell you how much charge is enclosed because of that rule about the lines coming out being proportional to the charge. And so that's what Gauss's law is. Gauss's law says that the electric field strength coming out of a surface is proportional to the charge held inside. How do we do this? Well, first we have to introduce this thing called flux. Where's the word flux? It doesn't have the word flux here, but this is what the flux is. The flux is the electric field strength going through a surface. So we calculate the flux by taking the area of the surface and finding what portion of that area is perpendicular or normal to the electric field, and then integrating over the surface. So we have an equation to calculate this. If you were in the algebra-based class, you would have the flux is equal to the electric field times the area times cosine of the angle between the two, which works perfectly well if you have a flat surface. If you have a surface that's varying, well, then you have to do an integral. And so we have something that's a little more complicated. I'm sorry, my equation got squished here. The electric flux, so this is the symbol for electric flux. That is phi, the Greek F sound. A subscript E, because later on we're going to talk about magnetic flux as well, is E dot dA. Well, it's the integral of E dot dA. So this is the calculus definition here. Electric flux is integral of E dot dA. So what we're going to have to do is find the electric field vector and the dA area vector, and then take the dot product between the two and integrate. And you look at that and you say, well, that has the potential to be difficult. It does. In most cases, we are going to choose situations where we have a symmetry that makes this simple. So you don't actually do the integral simple. So Gauss's law becomes hard to do in most cases where it's not this. There are cases where you can do it. We might have a homework problem that has you calculate the flux where you actually have to do an integral. But in most cases, we're going to choose a symmetry so that we have the angle between the electric field and the area is either 90 degrees or 0 degrees. And if the angle between the two is 90 degrees, what do you get for the dot product?
Dot product is 0.
Dot product is multiplying the parallel part. So if they're perpendicular, it's 0. And if they're parallel, if E and dA are the same direction, then it's going to be 1. Yeah. So that's what we're going to do in most cases. Now, Gauss's law, now that you know how to calculate the flux, says that that flux is equal to the charge enclosed by the surface divided by epsilon 0, the permittivity of free space. So it's actually a real simple relationship between the charge enclosed and the electric flux. Now, when you use this equation, you are going to calculate the left side independently from the right side and then set them equal to each other to solve for the unknown. I've had students who try to do a circular argument to make an equation for the left side and then just say, so I have the right side in terms of the left side, so there's my answer, and not actually solve for the thing you're supposed to solve for. Right? There's going to be something you need to find. You can't find your answer in terms of that thing you need to find. So this is a case that it's much better to actually do this than it is to look at the definition. So here's how to do problems in the homework set. I have now covered all but one of the pieces you need for the homework set. One problem uses the differential form of Gauss's law. The differential form, this here is the integral form. You see that we had the flux was an integral, and so it's the integral form. The derivative form is I think that, wait, there's, I'm pretty sure that's the derivative form. And so for one of them, you're going to do that. What is this symbol here? It is a directional derivative. It's the gradient in Cartesian coordinates, which is all you're going to have to use for the homework problem. That's x hat d dx plus y hat d dy plus z hat d dz. Now do keep in mind that I wrote this down just from memory. That minus sign could be wrong. Can one of you actually look up the derivative form of Gauss's law, just because I don't want to leave it here and not have the correct form. I totally forgot to look it up before lecture. I'll go on. Pay attention when you have to, and when you're bored, you can continue to look. But I do want to find it. So with the homework problems, some will use Coulomb's law, some will use Gauss's law, one will use the derivative form. How do you know which law you use? If there is an exploitable symmetry, then you use Gauss's law. And when it asks you about assumptions, your assumptions are going to be about that symmetry, how you're going to be able to use Gauss's law easily instead of it being difficult. So questions, just show of hands. What type of exploitable symmetry does a sphere have? It's this close to a rhetorical question. What does it have? Spherical symmetry. Now, we'll do a problem and then hopefully understand this better as we move on. So what is the flux through a sphere of radius r equals 5 centimeters that has a point charge of q equals minus 2 microcoulombs at its center? That's not a full problem. That's just asking what the flux is. So there are two ways you could find the flux. One would be to use the equation for flux, and one would be to use Gauss's law. So let's look at this. The standard way of finding the flux. Integral of electric field. That was perfect. Dot dA. If I have a sphere with a charge right at the center, then I have a special symmetry. If the charge wasn't right at the center, I wouldn't have a special symmetry, right? But if I have this special symmetry of a sphere that is centered on the charge, then I can make the assumption that anywhere on this surface, I'm going to have the electric field pointing directly, since this is a negative charge, what direction is the electric field supposed to point? Electric fields point blank to negative charge. Into. So the electric field is pointing into. So anywhere on the surface, electric field is into the surface. What direction is the normal to the surface? By definition, the area is in the normal direction, and so the area is out of surface. So the electric field is always in, the area is always out, so the flux is going to have to be I'm going to put the electric field, since it's a vector, I'm just going to leave this as a positive and let me have a negative electric field to say pointing it. So electric field times d area because the angles between the two are 0 or 180. But then I have my second symmetry argument. So this was based on by spherical symmetry. Parallel or anti-parallel to dA. So that was my assumption number one. Now assumption number two, if I have spherical symmetry, I can't tell the difference in any location on the sphere. It's still going to be the electric field is either going into or out of the sphere, and that's all that matters. The electric field strength can't vary as you move around the sphere a constant distance from the charge. just based on symmetry. It doesn't matter that you know Coulomb's law for either of these. Based on the symmetry, you're going to have E is constant on A due to symmetry. So if the electric field is constant, that means my integral is E integral of dA, but by definition, what's the integral of dA? Area of a sphere is 4 pi. Wow, my 4 looked like a pi, and so did my pi. 4 pi times radius squared. So the flux is going to have to be E times 4 pi radius squared. My calculus disappeared. I was able to solve the integral of a dot product between two vectors by making two assumptions based on the spherical symmetry. So my flux is equal to E times 4 pi r squared. But then I have the other way of calculating it. The other way of calculating it is using Gauss's law. It's the charge enclosed over epsilon 0. How much charge is enclosed by that sphere? Okay, I'm going to put Q here because it's quicker. So it's just that charge. So this is one answer for the flux. This is the other answer for the flux. What do you usually do with this? You either calculate the electric field based on how much charge is enclosed, or you calculate the charge enclosed based on the electric field. So in this case, because I gave you the charge enclosed, we would calculate the electric field. So if I set these equal to each other, I'm going to have electric field times 4 pi r squared is equal to Q over epsilon 0. Solve that for electric field. And I have the same result that I would have gotten from Coulomb's law. Now, I didn't put in any of the numbers here. The numbers were there to give you something concrete to think about. But what matters is being able to do this work. Now, in your homework problems, you're going to have numbers. And so you'll be putting in the numbers to get, answers as you work your way through. Actually, you're going to have numbers. You can have equations and symbols. So what was the key of what I just showed you? What was important about what I showed you in this slide? That was the key. We're using symmetry to solve what otherwise would be pretty difficult integrals. And I can skip right over that. I can skip over that too. So next question. Oh my goodness, I'm out of time. What type of exploitable symmetry does an infinitely long straight wire have?
Yes, planar.
Has cylindrical symmetry. Because if you put a cylinder around it, you're going to see that everything looks the same. Doesn't matter where you are on the surface of the infinite cylinder. Has to be an infinite cylinder to go with the infinitely long wire. If it's not infinitely long, your symmetry breaks. So,
I'll go ahead.
So if you have a problem that has a wire, or as you have in your homework, a cylindrical distribution of charge, then what you're going to have to do is make a different symmetry. Now, the last thing that I have to cover, because when you do these problems, it's an important step, is the term Gaussian surface. In the problem I did up here, I said, what is the flux through a sphere of radius r that has a point charge at its center? That sphere of radius r was not something that actually was present. It was just an imaginary surface. That is what a Gaussian surface is. A Gaussian surface is an imaginary surface on which you are going to find the electric field. And so it's not a real surface. You make it up, and you choose that surface's shape to match the symmetry. So for the point charge, we chose a sphere because of the spherical symmetry. For a line of charge, we're going to use a cylinder because of the symmetry. But then comes the trickiest part. I have a line that goes on forever. I am not going to make my Gaussian surface infinite in height. I'm going to make my Gaussian surface. It has to be concentric with the wire, but just have an arbitrary height h. What direction should the electric field point? Let's say that this wire has a positive charge. What direction should the electric field point? It should point like that. So if we look at my Gaussian surface, what direction is the area on the top of my Gaussian surface? What direction is the area on the top of the Gaussian surface? It's, well, parallel to the line, it's vertical. And what direction is the area on the bottom? Well, yeah. So there's the areas there. What about on the side? What direction is the area on the side of the cylinder?
Well, yeah, is it perpendicular or is it normal?
Normal. So my dA vectors on the top and bottom are 90 degrees from the E vectors. So if I do the dot product on the top of my cylinder, what is dE? What is E dot dA? If E is horizontal and dA is vertical, what's E dot dA? 0. So the flux on the top is 0. The flux on the bottom is 0. On the sides, E is parallel to dA, so E dot dA is just E times dA for the side. And so we're going to have just the side now that we have to worry about. And then we have the second argument based on symmetry that at a constant radius from that wire, you're going to have a constant electric field. So integral of E dot dA is going to be E times the area for the side of the cylinder.
Do we have normal lab today, or we're just doing the group thing?
It's just the group thing. No quiz, no. So I don't remember which group you're in.
I thought we choose.
Huh?
I thought we choose.
3 of the groups have already been chosen, which means the 4th one is chosen by default. I thought that you were in one
Christian.
of them.
Noah, Christian, Jeff, and me are in the same team. We just need one more person.
I can tell you who that is. Let me stop the recording here.